So this is NOC 26EE168 Semiconductor Devices on Circuits. The course instructor is Professor Sanjiv Sambandan from IISc. I am Debashish from IIT Kanpur. So there are two tutorial sessions in this course, or TA sessions. One will be on this one every Saturday from 3 to 5, and another one will be mostly on Sunday. I'm not sure if the time has been shared. I think it is probably from 6 to 8, right? So these two will run parallelly. So you may find some overlap in the sessions. So after a couple of weeks, you can decide, right? So before we start, so let us have a quick introduction. Okay. So should I call out names and you will introduce yourselves, or how do I go about it? I just wanted to check that in which curriculum you are and in which background you have, right? So it will help me to understand till what depth I should go into to explain the topics.
Good afternoon, sir. Myself, I am Anjali.
Good afternoon.
Yes, sir. So this course I have taken regarding to my PhD coursework.
Okay, so where are you doing your PhD?
I'm doing in NIT Andhra Pradesh.
Tirupati.
No, sir, Andhra Pradesh.
Andhra Pradesh. Okay.
Yes, sir.
Okay, fine.
Yes.
So what is your PhD topic?
My PhD topic is not decided yet, but
Okay, you have just joined.
yeah, yes, sir. This is my first year.
Okay, good. See if anyone else is- So anyone else? So let me put it this way. Anyone else from undergrad background, those who are doing this course in undergraduation?
Hello. Hello.
Yeah, yeah.
Hello, sir. My name is Janakadatta. I
Hi.
am a, I am an undergraduate student
In which year you are?
in Telangana state, sir.
No, no. In which year you are in your study?
Second
First
year.
year's second year.
Yes, sir.
Okay. You are in EE or ECE?
EC, sir.
Okay. So anyone else from undergraduation?
Yes, sir. Hello.
Yeah, hi.
Yeah, myself, Likit. I'm
Hello.
currently pursuing third year,
Okay.
and my branch was CSC AML.
So why are you doing this course then?
I have been to from minors, honors minors are there, right?
Ah, okay. So
So
ECE
have
is
been,
your minors, right?
yeah,
Okay. So I think we have a mixed batch, right? And most of the others should be from PG student.
yeah.
Okay. Okay, fine. So I think we have people are still joining. Okay. Maybe we'll take couple of more. So anyone else wants to introduce themselves? Or anyone wish to volunteer? What are the expectations from this course? Anyway, so let's start it. Okay, another one. So as you know that this course will start from basics of quantum mechanics to the basic circuits, right? And that bridges the devices, semiconductor devices. So a little bit about the course. So uh, semiconductor devices, as you know, that these devices are running almost everything that you use today, right? Whatever software you are using today, the data are being processed at some data centers that are situated long at long distances, and where all these CPUs and GPUs, right? Those things are situated for processing your data, and that processors are essentially made out of MOSFETs, right? Or transistors. So these transistors are made of these semiconductor devices. Fine. So anyone wants to tell that what is so beautiful about semiconductors, that we are studying semiconductor devices? Why semiconductors we are discussing and we are fascinating so much about, right? You must have heard about India's semiconductor mission as well, right? The government policies surrounding semiconductors. It is not a hidden fact that the countries, those who are controlling the semiconductor supply chain, and believe me, it is not a single country. The entire supply chain is dependent on a collaboration of multiple countries. So why these semiconductors? And whoever has this edge over semiconductors or advantage over semiconductors will essentially do well, right? So why these semiconductors? What is so fascinating about them?
So that semiconductors have less power consumption.
No, power consumption. See, if you are talking about power consumption, no. Let's say if you have any block, right? You apply some voltage around it, okay? So current will flow, right? So there is nothing called ideal metal, right? So there will be some resistance, and your I square R loss will be there, power consumption will be there. So what do you mean by less power consumption? Which one you are reducing, I or this R, right? It is not that that is not the reason why semiconductors are being used. So essentially, what do I think most of you have done digital electronics course, right? Or a basic electronics, you are familiar with zero, one,
It-
Boolean algebra, and so on,
It's
right?
because it has ability to act both as conductor and this thing insulator. So we can
Right,
use, yeah, we can use semiconductor integrated for information as zeros and ones and like for
right.
chips
So
and all. This thing.
basically, what you are saying, that if it is conducting, right? So people are still joining. So, okay, wait a second. Yeah. So if you are letting the current pass through a material, let's say you have a black box, okay? Let's say you have a black box, you have two terminals, you are letting the current pass, you are applying some voltage here, you are letting the current pass and probing it at this terminal, right? So that state you can consider it as one or on state, and you are prohibiting it from uh, current conduction, so there is no current coming out, so that you can consider it as off. So basically what you have said, that semiconductors, the basic thing is we can control the current flow through it by tuning its what we call is conductivity, right? Conductivity. So you know this Ohm's law, right? Resistance is rho of L by A. This rho is 1 over conductivity L over A. And what is this conductivity? If you blow up the conductivity, so it comes out to be your charge times free carriers, let's say N, times the something called the mobility of the carriers, right? So what you are controlling, once you fix a material, most of the time this mobility is basically fixed. Fine. Mobility means ease of flow. So let's say I have chosen either my semiconductor to be, let's say, silicon carbide, or let's say I have chosen it to be silicon, or let's say I have chosen it to be germanium. So my mobility is almost fixed, right? So what I am tuning, I am basically tuning this N by, I should set a timer anyway. So I am basically tuning the free carrier concentration in the material, right? And by tuning N, I am tuning my sigma. I am tuning my sigma. Once I am tuning my sigma, I am tuning this rho, and effectively I am tuning my resistance, right? That is why how semiconductor plays an important role. Fine. Basically, I can create an on and off state by just having a control over the conductivity of the material. That is why semiconductor is so much important. And what is the another advantage? That it comes in a very small size, right? So I can make over a small area very large integrate stuffs, right? Integrated circuit and all will come about, will come to that, right? Why it is called integrated circuits, and what are the difference between the breadboarding you are doing in your undergrads, right? So this is what semiconductor is in a nutshell. And these devices and circuits are basically the next step. So basically you have your materials. By this manipulation of these materials, we'll see what doping and other things are. Through that we make some exotic, let's say we'll have this p type doped, n type doped materials, and by combination of this and oxides of the semiconductors will create some devices, right? Devices, let's say your pn junctions you can create. Then you can create your, let's say, bjt, right, three terminal device. Then you can create your MOSFETs, right? They say N regions, P region, then some oxide, some poly, and you can create MOSFETs. Okay. Then once these devices are created, then by combination of these devices, we can create circuits. Okay. And this is the that is a circuit what is very close to what we are familiar with, or what we are using in on at a daily basis. Fine. But our learning should be from bottom up. That means first we'll learn how about the materials, then we'll learn about the devices and circuits. This is how the course is designed. So any question till this point?
No, sir. Thank you.
Okay. So this is just brief about the course. So yeah, another thing. So why we are bothered about this, quantum mechanics? So I am sure that this quantum mechanics should be somewhat scary to many of you, if not all of you, right? So why we are studying this quantum mechanics?
Due to the disadvantages of the classical physics.
Yeah, but you see, you study this Bohr's atomic models and all, right? Those are not quantum mechanics, right? Those are basically your classical mechanics. You discuss about your angular momentums, and then you discuss about your centripetal forces. You balance it out to get the Bohr radius and so on. So quantum mechanics is basically, there are certain phenomena which we cannot explain by the classical mechanics. As we go to lower dimension means we will go into the dimensions of angstrom, right? You will see the units and the scales. Just if you carefully note whatever the results you are getting in your quizzes, uh, just note the units. Like maybe 10 to the power minus 31 kilogram, right? 10 to the power minus 31 kilogram, one electron, 9.11 times 10 to the power minus 31 kilogram. Note that how small it is. Similarly, the distance over which will be considerate about will be very small. It will be in the nanometer, angstrom range, those kind of ranges, right? So in that those low dimensions and low mass objects, classical mechanics seem to deviate, right? I will not say fail, seem to deviate, right? So that's why your notion of quantum mechanics become very important. So if you are interested in learning the basics of quantum mechanics, I'll suggest that have a curiosity and go out to the browser web and check in your Wikipedia pages, right? You will see a lot of good visualizations, which may be very difficult to get in a 2D plane of your books. Fine. So these are the prerequisite of the course. So I'll expect that if you want to follow the session, whatever we'll discuss here, so it is better that you come prepared with just reading the lectures once, right? Let's say for week one, you should be able to cover at least the week one lectures and have an attempt to the assignments as well. So that if you have any doubt, you can ask in this session. Fine. And yeah, this session is being recorded and it will be provided to you by the NPTEL team. So anyway, let's start then. So the first question, it is asked that the wave function of a particle must be normalizable, right? So today we'll be basically dealing with quantum mechanics and Schrodinger equation. Fine. I hope that is the content of your week one in the actual lecture series, right?
Yes, sir.
So what do we mean by wave function? What is this wave function? We know it as this guy, right? This is a function of space and time. So what is this? So what is wave about it? What is the term wave about it? So just tell me if you have heard of these two stuff. And are you aware of these two? The first one is your Planck's hypothesis, right? What does it say? Let's say another way of representing this is H bar, we call it H bar or a reduced Planck's constant, that is your H by 2 pi and times 2 pi nu or 2 pi f will give you the angular frequency, right? So this is a way of representation. And this one, lambda equals to H by P, P is your momentum. So often it is written as H by mv, right? So we'll refrain ourselves from writing it this way. So this is your momentum and this is your wavelength. So this particular relation gives you the notion of wave particle duality. Okay, so wave particle duality means there is a wave associated, wave nature associated with any particle. Okay, so this is called de Broglie's relation. Fine. So based on these two notion or these two laws, so Planck's hypothesis, by the way, is just an fitting routine. I don't know if you know what fitting routine is. That means you observe some phenomena, you plot it in a curve, and then you try to formulate a formula out of just pure observation, right? This is called phenomenological observations, right? Planck's formula is just that. It so happened that it became true later. So far, we have not found any deviation of it, but it is not that much rigorously proven. Fine. So, based on these two notion of de Broglie's hypothesis, de Broglie's relation, and Planck's hypothesis, in 1926, developed some mathematical nature of this. They called it quantum mechanics, or the study of dealing with small particles. Okay, so this psi was basically, you can consider it as a state variable, of a quantum system. So what is a state variable? A state variable is something which evolves over time and explain about the overall nature of the entire system, right? Fine. That is what is called a state variable. So what this psi actually gives you is gives you the notion of probability. Probability means, let's say you have some space, okay, and if we ask you that, let's say there is a very tiny particle, and if someone is asking you that what is the probability of finding this particle in this exact position, we'll see how these things are related to the actual world, right? It does not make sense if we just talk about what is the probability of finding a particle or probability of seeing a cat inside a box, right? It doesn't make sense. We'll see how this is related to the actual world scenario, but for the time being, uh, understand it this way, that this psi is something related to do with probability, right? It is not exactly your probability, but it has something to do with probability. Okay, probability of finding a particle in a particular location. So this psi xyz t means probability of finding a particle in this particular position xyz at time t. Fine. So this is kind of an mathematical abstract which does not have much significance, but what does have significance is this quantity, psi star psi. So I am using psi star means I am using some kind of complex conjugate, right? This gives me directly the notion that psi is a complex number. Okay, a complex number is something which has real and imaginary parts. So this psi star psi gives you what? It gives you the probability density function of that particular particle. Okay, fine. So far we have this quantity psi star psi, right? What do we know about probability density functions? If I integrate a PDF, let's say f of x or probability density function over all space, then I should get 1, right? It is same as if I am flipping a coin, then I can have either head or tail, right? And if I just add the probability of these two, I should always get 1. That means something has to happen, right? Similarly, if I integrate this probability density function over the entire space, V stands for volume, and integrate it over dV, so it gives me 1. What does it mean? This particular quantity means probability of finding a particle at a location XYZ, right? Now what I am saying, in entire volume, what is entire volume? Let's say in a system, in a closed system, in the entire volume, the particle has to be present somewhere, right? So if I integrate the probability density function over the entire volume, I should have the total probability, that is 1. That means the particle has to exist somewhere. We don't know where it is, but it has to exist somewhere, right? So this particular integration is basically a 3D integral. If I write it in a blown up version, so this will be dx dy dz equal to 1. So x equal to minus infinity to infinity, y equals to minus infinity to infinity, z equals to minus infinity to infinity. In an unbounded system, then I am considering the entire space, right? The particle has to be present somewhere. Fine. This particular integral is called normalization integral or the normalization condition. Fine. So the question should be, what is normalization in this? Normalization means what? Let's say I have total, let's say I have 5 buckets, right? 5, 4, let's say 3, 2, 1, or let's say 4 buckets, 4, 3, 2, 1, right? And if I want to say find out the normalization, one way I can do it is, let's say I say that this is 4 over 10, 3 over 10, 2 over 10, 1 over 10. I have just added the total number and then normalize it with the total number. This is basically what is called normalization. Dividing the quantity by the total quantity. So what is normalizable about this integration? Can anyone try to volunteer why it is called normalization integral? Where is that normalization thing coming from? Anyone?
Or maybe to normalize it with respect to the dimensions of the uh, object.
No, we are integrating it with respect to the entire system dimension, right? We are not normalizing it. So anyone else? Where is that
Sir, to
normalization
make
part
the
coming
value of the
from?
integral 1.
That is fine. That is the consequence of the normalization.
We
See,
are
normalization means dividing by the, again, normalization means dividing by the total. So where is that dividing by the total thing coming in this integral? You know, right? This is called normalization integral from the lectures.
Yes, sir.
Fine. So have you ever pondered about why it is called normalization integral? Normalization, I think I have made it clear. If someone has any question on that normalization part, you can ask. Normalization means dividing by the total. What is probability, by the way? What is the basic definition of probability?
number of time that event has occurred by the total possible events, total events maybe. So are we trying to compare that if the particle is present in the total system?
Okay. So probability you have correctly pointed out. So see, this particular stuff is PDF, right? Probability distribution function, which itself is normalized. Is it clear?
Yes, sir.
So that is why, when let's say probability of having the particle in this box is 4 by 10, right? This is this. Now, if I tell you that you only have these 4 boxes and the particle has to be present in some of any of the boxes, then what is the probability of finding the particle in any of these boxes? What will you say? You will say just it will be 1, right? How will you compute that? You will add the individual probability and it will come up to be 1, right? That means the particle has to be present either here or here or here or here. Fine. So how will you write that? You will write, in this case you call it probability distribution function, not density function, because it is not continuous, right? You have discrete boxes. So summation of all probability, this is the fundamental rule of probability. Summation of all probability distribution functions should constitute out to be 1. Now think that you, instead of having these 4 boxes, you have infinite small boxes, right? Then by the notion of integration, what will you do? You will just open it up and this entire thing will become 1, right? This is called the normalization integral. That means the particle has to be present in any of the boxes, that is for sure. In which boxes, that is the matter of randomness or the matter of probability, probable ways of finding the material. That will be dependent on what are my boundary conditions and how the governing laws are, right? That will come to. But from a top view, we know that if this quantity denotes the probability density function of finding a particle in a volume dV, then if I integrate this volume, means the small boxes over all boxes, so the particle has to be present somewhere, right? So this is called your normalization integral, and that normalization part is coming from the basic definition of probability. That probability by itself is normalized by the total number of possible occurrences. Is it clear? If you have any question, you are free to ask.
Sir, can you give me a brief recap?
Okay. So what we were, the question stated that the wave function of the particle must be normalizable, because so we first started with what the wave function is. So the wave function is nothing but a, if I have to take something, the key takeaway points is wave function is nothing but a mathematical abstract, right? It gives you the notion of probability, but not exactly the probability. This psi, the wave function, it is a state variable of the entire system. That means if I know this psi somehow, I can construct multiple blocks out of it and see what are my measurable quantities, right? When you read MOSFETs and all, later you will see there is something called surface potential, which you cannot never measure in physical domain, but that works as a state variable of the system. Fine, it is in the similar notion. Now what actually holds a meaning is the psi star psi, that is the complex conjugate of the wave function, dot product of that with respect to itself. So another way of writing this as this, mod of psi square. Psi is a complex number, so this gives you the notion of probability density function, right? So what is probability density function, that we have tried to explain it with this example, that let's say we have 4 boxes and the probability of finding a ball, let's say, or a particle in box 1 is 4, and other is 3 to 1. So the total number of occurrences becoming 10, and out of 10 times, 4 times I can find the box in this box, ball in this box, 3 times here, 2 times here, and 1 time here. So of course, by the notion of probability, you know that the finding of probability of the ball in this box is 4 by 10, then 3 by 10, 2 by 10, and 1 by 10, right? Now if I ask you a simple question, that what is the probability of finding the ball in any of these boxes, right? So then how will you do that? You will just add the individual probability, right? Because I have used the word any of these boxes. Fine. So then it will constitute out to be 1. So this particular thing is called normalization integral once we convert it to the continuous domain. How do we convert any discrete domain to continuous domain? We divide it to very small values. right? And then sum it up, and then the summation becomes integration. Fine. Similarly, if this guy gives me the probability density function of finding a particle in a particular location or particular volume, so if I integrate it over the entire volume, I should be able to say that it will constitute out to be 1, because the particle has to be present somewhere in the space, right? It is the same analogy that the ball has to be present in any of the boxes, right? So this particular thing is called normalization integral. Okay, and the term normalization or the division by the total occurrence is coming from this your the notion of probability. Fine. So if I look at the options, so the particle momentum must be conserved. The particle cannot exist at two places at the same time. The particle must exist somewhere in the space. So the normalization integration or normalizability or normalization integral gives us the notion of this one. The particle must exist somewhere in the entire space, right? Fine. Okay. So, and what about the other options? Momentum conservation is has nothing to do with normalization integral in the first glance. Where does this momentum conservation comes from? And also charge must be conserved, that is also not part of this, because we're not talking about any charges. That particle may be uncharged as well, right? Electron, for example, is a charged particle. Phonon, for example, or photon, you must be more familiar with photons. The particle constituent particles of light is not a charged particle, right? So the particle cannot exist at two places at the same time. This also is not revealed by the normalization integral. So the correct option is this. So by the way, do you know how this laws of conservation comes about? Momentum conservation and this charge conservation. Why momentum is conserved? Why charge is conserved? Why energy is conserved for that matter? So I'll just name something. You can just, if you are interested, just search this uh, in your any AI models or chat GPT, Google, whatever is not, you will get to know how this laws of conservations comes about, right? This comes about from the symmetry in nature. Okay, I'll not discuss much on this, but you can go and check this out. So you'll get a more better feeling about how this laws of conservation have come about. Okay, so let's move on to the next part. So the question is, which of the following is not a valid quantum mechanical wave function, right? So what we have studied so far, that psi is a function of four independent variables, right? Now let's say we are concerned about in one dimensional space. What is in one dimensional space? A line is in one dimensional space. So you can move along this direction or this direction, right? This is in one dimensional space. A two dimensional space is any plot you make, right? You can move this direction, or any direction in between. 3D is what is the real space, right? We are we live in, right? So in this case, whenever you encounter psi of x, like in this question, you understand that we are discussing about a one-dimensional space only, right? So the question is, which of the following is not a valid quantum mechanical wave function? So that means what? The quantum mechanical wave function, for it to be valid, it has to obey certain principles. So can you name those principles from the lecture series? Properties of psi, or the state variable, or the quantum mechanical wave function of Schrodinger's quantum mechanics, right? What are the properties of psi? Anyone?
It could be finite, continuous.
Let's go one by one. It has to be, first thing is single valued and finite, let's say. Okay, finite means it does not blow up, right? It does not shoot to infinity. Fine. And what is the other thing you have mentioned? It has to be continuous.
It's continuous.
Continuous. Any other thing? Does it have to be differentiable?
Yes, it has to be differential.
It has to be differentiable. So by the way, what is the difference between continuity and differentiability? So is this function continuous? So let's say this is x, this is f of x. Is this function continuous?
No, sir.
Why not? Let's say at this point x equal to x naught, is this function continuous? So what does continuity means? The left hand limit and the right hand limit should be equal, right? So let's say you are a person riding, let's say this is a ramp kind of thing, right? You are riding on top of this, and at this point you reach this point. Now let's say another person, that is your right hand limit, the red one is your left hand limit, the green one is your right hand limit, is again riding up the ramp, and at x0 it will also reach the same location. Why it will not be this, why it will be discontinuous? It is continuous, right? Is it clear?
Yes, it's clear.
But it is not differentiable, right? Because if you take the derivative of it, so okay, just let me make these points very clear. So let's say it is x equal to x0. So what is the derivative of the first part? It will be some constant line, right? And what is the derivative of this part, second part? It will be some constant line in the negative axis, right? So the derivative exists till this point, and at this point we can see there is a jump, so the derivative is not continuous, right? Is it clear? So the slope of this is positive, tan theta of this, tan theta of this is negative, that is why this is positive and this is negative. It is a linear function, so derivative will be constant, right? But at the point x equal to x0, you will have a discontinuity. So that means fx is continuous, but f dash x is not continuous. Fx is not differentiable at x equal to x0, and forget about this f dash x. It is a derivative of this will be, by the way, what will be the derivative of this? What will be f double dash x? How will f double dash x look like? Let's say this is your x naught. So till this point, a constant line's derivative will be 0. Another constant line derivative will be 0. So slope of this is 0. Slope of this is 0. And at this point, the derivative will be a negative delta function, right? Is it clear? Anyone who have not understood this part? Because this will encounter later in today's session. So I want you to understand continuity and differentiability very clearly, right? And these all are the concepts, whether you have covered it in your +2 level or in your signals and systems course. Is it clear? The three plots?
Yes, exactly.
Okay. So the properties of psi is that single valued, finite, continuous, differentiable, and also this psi dash, or the first derivative of the wave function, or d psi dx, should be continuous and preferably differentiable. Okay, we'll see that this is not always true, this differentiability, this differentiable psi dash to be, or the derivative of the wave function to be differentiable, it may not be always true. We'll see the how physically this is not true in some cases, but anyway, these are the conditions, right? Now, given in this plots, we have, these are the boundary of my system. Okay, so what we have to consider it about is between these two blue lines, because wherever your psi s is 0, so let's say wherever your psi of x is 0, so your psi star psi, or the probability distribution function, will also be 0. That means the particle does not exist at that point. So that is why this 0 parts we are excluding from the system. So this is not part of the system, we can safely exclude. Is it clear why we are excluding this other parts and considering our system to be inside this only, right? Now we have to check whether any of my desired properties of psi is violated or not. So what are the properties of psi? Single valued, finite, continuous, differentiable, and also from the previous question we know that normalization condition has to be satisfied, right? Within the system, the normalization condition has to be satisfied. So can you tell me which one of the function is not satisfying some of the properties? Yeah,
So the fourth one.
the fourth one, right? So this is continuous, sine curve, differentiable. This is also continuous, also differentiable. This is continuous, differentiable, right? Normalization integral can be made valid in any of this, right? So this one we can see that first of all it is not continuous, because at this point, let's say x equal to 0, my left hand limit and right hand limit are not same. So it is violating the continuity condition. Fine. So this is why this is not a valid wave function. Fine. Sorry. Yeah. So if that is clear, let's move on to the next question. The ratio of maximum and minimum intensities in an interference pattern is 25:1. Then the ratio of the amplitude of two interfering waves will be. How do we go about it? So interference means two waves are superimposing on a similar space and getting added, right? Interfering means they are getting added. Then depending upon their phase over the space, they can make constructive interference or destructive interference. Fine. That will give me the peaks and valleys of the interference pattern, or the maximum intensity or the minimum intensity. Fine. So let us consider two waves. So let's say my one wave is a a1 sine omega t. Fine. Time varying wave we are considering. Let's say my another wave is a2 sine omega t plus phi. So I can have omega 1 t and omega 2 t, right? And this omega 1 t minus omega 2 t equal to phi, that I can consider. But for the sake of simplicity, we are considering it this way. These two are different, two different waves. Fine. Now we have to make them interfere. That means what? We have to add them up. So the total wave will be sum of these two. That means your a1 sine omega t plus a2 sine omega t plus phi. Now break this up. So A2 sine omega t cos phi plus A2 cos omega t sin phi. Now let us take defer this sin omega t at the same place. So 1 plus A2 cos phi sin omega t plus A2 sin phi cos of omega t. Now let's say the overall wave has an amplitude of A and it is sin omega t plus theta, right? This is the overall interfere wave. Overall interfered wave. So then you will have A cos theta sin omega t plus A sin theta cos omega t. So you note that this part is this one and this part is this one, right? Now what is intensity? So let's say, okay, so let me just tell me what is my intensity of the first wave. How is intensity related to the amplitude of the wave? Intensity is nothing but it is proportional to the amplitude square, right? Are you aware of this fact? Intensity is proportional to the amplitude square of the wave. Similarly, this I2 will be proportional to A2 square. Fine. So what will be the intensity of this interfered wave? I will be proportional to A square because A is the amplitude of the wave, right? So now I want to find out A square. Then I should do this, and this will give me A1 plus A2 cos phi whole square plus A2 square sin square phi. So what we are trying to do is we want to express the intensity of the interference wave with respect to the amplitude of the incident waves, right? This is my one incident wave, this is my another incident wave. I want to express A square in terms of A1 and A2. That is the agenda. So if I do that, then I will have A1 square A1 A2 cos phi. Then this A2 square cos square theta and A2 square sin square theta will give me A2 square. Fine. Now my I max is proportional to A max square and I min is proportional to A min square. So I need to find out A max and A min. This is my A. So A max will be what? Maximum value of A1 square plus A2 square plus 2A1 A2 cos phi, right? What is the maximum value of this? That will depend on what? The maximum value of cos theta, right? Or cos phi. That is my plus 1. So this will lead out to be A1 plus A2 whole square. Fine? Because the maximum value of this guy is 2A1 A2. Similarly, the minimum value of cos phi is minus 1. So that will lead to A mean square is A1 minus A2 whole square, right? So that means my I max over I mean will give me A1 plus A2 whole square divided by A1 minus A2 whole square. And this I max by I mean is given as 25:1, right? So that will lead me A1 by A2. So it will be square root of this 5 by 1, then 5 plus 1 minus 5 minus 1. So 1.5. Okay. I think a similar problem is assigned to you as part of the quiz. So if you have followed this clearly, so you'll be able to solve that. So any doubt in this? I think this was pretty straightforward.
Yes, sir.
Okay, so let's move on then. Okay, in this question, it is asked that in electron beam lithography, patterns are exposed to electrons. Patterns are exposed with electrons. The small wavelength of electrons helps to achieve small feature sizes in orders of nanometer. Assume an electron gun of energy this. What is the wavelength of this electron? Fine. How do you go about this? What is this electron beam lithography? So, how many of you are aware of this thing? What is lithography? So, lithography basically means making pattern over some stone, right? In this case, what stone we are talking about is the silicon wafer. So if you have seen the silicon wafer, it is like a long ruler kind of diameter, 300 mm or 12 inches, and on top of that you shine your light, okay, shine your light, and by some shaded and unshaded area, we call it mask. You create patterns over it, right? This particular thing is called photolithography. Now, instead of light, you can use electron beams as well, right? High energy electron beams as well. So this, then we call it electron beam lithography. So in that case, you will have your silicon wafer, you will have some electron gun, which are emitting high energy electrons, and you are passing it through some mask and multiple layers of lenses to create high numerical aperture, and then create some painting on top of the stone or lithos. That is what is called electron beam lithography. Fine. Now the question is, this electrons what we are emitting as a kinetic energy of 50 kilo electron volt. Fine. And they want us to find out the wavelength of the electron. How do we do that? So you know your energy is nothing but h nu, right? It is known, right? H nu. This is Planck's hypothesis. We have discussed sometimes back. So this h nu, you can write it as C over lambda, right? And this E is nothing but your half mv square, or the energy. From this you can find out your lambda. But can we do this? Can we do this? What is the issue in this? Anyone? Let me put it in this way. Another way is your energy, you have half mv square, that is your half m square v square by m square v square by m, that is your p square by 2m. This p square you can write as h bar square k square by 2m. This h bar square by 2m, k you can write as 2 pi square by lambda square, and then you calculate from this. So which one should we follow, and why?
Is it the left one?
Why?
Because we are only considering it to be wave-like.
So here is also we have wavelength, right?
Yeah.
But what is the issue here? What is this C? This particular relation is valid for photons, right? Or relativistic particles. Fine. Your electrons will never move at a velocity very close to speed of light. So this simplification is just not valid. So you have to go via this route. Okay. So what are the things we have used there? This particular transition is nothing but your de Broglie relation. How? Your lambda equals to h by p, right? So p equals to h by lambda, that is h by 2 pi times 2 pi by lambda. This is your h bar, this is your k. So p is basically your h bar k. So this particular relation lambda equals to h by mv or h by p was not first invented by de Broglie. Okay, it was first postulated by Max Planck only. But what de Broglie had suggested and shown that it is valid for particle of any size. Fine. That is how this particular law has come to be known as de Broglie's relation. Fine. So electron, thus it is applicable as well as for photons, and same way it is applicable for electrons as well. But this Planck's law for relativistic electron being non-relativistic, we cannot use this direct simplification. Fine. Is it clear? So your lambda square has become this h square divided by 2m e. So your lambda you can calculate directly from h by h square by 2me. Fine. Can you quickly calculate and tell me? So lambda will be your 6.626 into 10 raised to minus 34 divided by square root of 2 times 9.11 times 10 raised to minus 31 times 50 kilo electron volt means 50 times 10 raised to 3 times 1.602 into 10 raised to minus 19, right? Meter. So if you simplify that, I hope you should get this 0.0055 nanometer. Okay. So is it clear not to fall into the traps of using this simplified formula, because this is not valid. Also, in the question, if you have seen, so wavelength was asked, but another point was mentioned that neglect the relativistic effect. What does it mean? What is the relativistic effect? Let's spend some more time in this question. So let's say on an silicon wafer, I want to pattern a dimension of let's say this is not to scale. So let's say this dimension is of 100 nanometer and there is a dimension of 2 nanometer. Okay. Can anyone tell me, let's say this is 2 electron guns are deployed. Let's say it has an energy E1, it has an energy E2. Which one should have more energy? To have a small feature size or a small line to be drawn, how to manipulate the electron beam? Should I increase the energy of the electron beam or decrease the energy of the electron beam? This is rightly sitting here, right? So these are my electron wavefronts. Okay. So to have a feature size of 100 nanometer or to print a feature of 100 nanometer, my electron wavelength has to be much smaller than this. Similarly, for 2 nanometer also my electron wavelength has to be much smaller than this. So let's say if this is lambda 2 and this is lambda 1, so lambda 2 has to be much smaller than lambda 1. These are the electron wavelengths. So what about E2? E2 has to be much greater than E1. Is it clear?
Yes.
Now, what is the consequence of this if I keep increasing my electron energy? So what is increasing? The kinetic energy of the electron is increasing. That means what? Kinetic energy is your half mv square is increasing. That means what? Your v is increasing. So v is approaching the speed of light. So this is what we talk about. This is what when we talk about relativistic effect. What is the consequence of moving very close to speed of light? What will happen to the mass of the electron? Will it increase or decrease? If it is moving at a very high speed, very close to light? For example, this 50 kilo electron volt, if you calculate, your V will come out to be around 1.1 into 10 raised to 8 meter per second. That is very close to the speed of light, right? But in the question it is mentioned that neglect this effect. So we have neglected. But what if this is not mentioned? So what are the corrections you have to do? You could not use this mass, right? This is the rest mass of the electron. So then what you had to use is your rest mass divided by 1 minus v square by c square. This is called Lorentz factor. So if your if v is much less than c, then your me is almost equal to m0. If v approaches c, then me is much greater than m0. So if you start moving at the speed of light, your effective mass becomes very high. Okay. So this correction you have to take into account then while calculating the answer if this particular thing is not mentioned. So it is always good to have a check that what is your V that is coming out to be and how close it with the value of C, right? And then again you cannot use this one even if it is approaching C because your M is also increasing. So it is not your photon like massless particles. Okay, you have to go through this route. Is it clear? So there are multiple pits where you can fall in this type of questions. So you have to be very careful about answering them, right? What are the approximations stated in the questions? And it is always to know the general solution than to know some particular solution. Okay. Is it clear?
Sir, can you explain the step p square by 2m?
So, hold on. Yeah. So this is E equal to half mv square, the kinetic energy part that is given in the question. Fine. Then E you can write from the kinetic energy P square by 2m from de Broglie's relation, or some of you may be calling it de Broglie's relation. This one is giving you this P equal to h bar k. So I replace that P equal to h bar k here. So it is h bar square k square by 2m. Then k I have replaced it with 2 pi by lambda, or you can directly put p equal to h by lambda, right? P equal to h by lambda you can put, and directly you can compute that lambda square is equal to h square by 2me, right? Then you find out lambda from this square root of h square by 2me. Then you have to have a sanity check that whether how much is the speed of associated with this kind of energy of the electron. If the speed is very close to the speed of light, then you have to involve the Lorentz correction. Then your ME will be different than M0 given in the question. Okay, because we have this approximation mentioned in the question, so we did not go for this much step. So our answer is directly found from this formula. Is it clear now?
Yes, sir.
Okay, so let's move on. Okay, so an electron in an infinite one-dimensional potential well jumps from the energy n equal to 4 energy level to the ground state energy level, and doing so it emits a photon of wavelength this. What is the width of the well? How to go about this? So what is mentioned, let's draw something. So let's draw energy, let's say electronic energy. Let us draw electronic energy in y-axis, and in x-axis let us draw the position. Okay, so let's say this is the well. So let's say this is x equal to 0, this is x equal to L. So how do we represent the well? We represent the well as this. So this is delta functions sitting at both the ends. That is giving me V equal to infinity. What is V? V is potential energy. So V is here potential energy. Fine. Now the question is, I need to first solve this system. Okay. So the question is, some electron is present here. Fine. And then as it is, you know that in quantum mechanics, the electron cannot take any arbitrary value of energy. Electron can take arbitrary value of energy only in free space, right? Where potential is zero and no force is being applied. Fine. But we are seeing that if we travel around the space, we see that there are two delta functions or infinite potentials sitting at two ends of the one-dimensional system. Fine. Try to visualize this. So think that this is a landscape. Let's say this is a landscape, some heart or home is here, right? And this is the earth level. And let's say somebody has dug a well in this location, right? And this well is underground, infinitely long. Fine. And somehow some person has slipped and is standing here at the bottom of the well. Fine. These all are earth. Now this is the same situation that this electron is seeing inside this one-dimensional potential well. Fine. So what are the laws applied in this case? Laws of motion, gravity and so on, right? But in a very small nanometer dimension, the quantum mechanical laws will apply here, and the system is governed by something called Schrodinger's equation. So Schrodinger equation, if I write, it will be something like this. So now tell me, how many of you understand what Schrodinger equation is? What is this? What is this? And what is this? This is your kinetic energy. This is your potential energy. And this is your total energy. Right? So Schrodinger equation is nothing but energy laws of energy conservation. Now, are you clear how this kinetic energy and potential energy came about? Or should I briefly tell you so that you will never forget?
Sir, can you please briefly?
Yeah. So what we have discussed so far is that psi is the system state variable, right? And it is a wave. Fine. And in quantum mechanics, you have something called operators. Fine. So what operators does? Let's say alpha is an operator. It works on a function. It creates a value times the function. So this is called quantum mechanical operator. This is your eigenfunction. This is your eigenvalue, and this is again the same function. So what in our case we do, this eigenvalue is basically the observables. Fine. In quantum mechanics, we have these operators are momentum operator, kinetic energy operator, potential energy operator, and total energy operator. Fine. And position operator. These are the 5 operators available. So let's say, and this function is nothing but your wave function. Okay. So let's say my psi has a form of a e to the power I kx minus omega t. Can I assume a wave to be of this form? I can, right? This is nothing but your sine theta plus cos theta, sine theta plus j cos theta, if you do the Euler's expansion, right? So this is a very general form of wave function. Okay. Now let me operate momentum operator on top of psi. So what should I expect? I should expect h bar k times psi, because this is the observed value, right? Why? We have seen, right, from de Broglie's equation, this is what we get, the momentum. Now how I want to construct what my p operator should be. So what my operator should be? So let's say I want to construct p of this equal to h bar k of psi. So what is my psi? Psi is equal to a e to the power I kx minus omega t. So I want to bring out h bar k times psi. So how can I bring out k times this? So I k times, so I k times a e to the power I kx minus I omega t. How can I bring this? By having this operation. Is it clear? I want k as a multiplication of the psi, right? And it is in the exponential. So I have to just differentiate it. So bring down the I of ik. Now I can just multiply both sides with h bar. Then h bar by I d dx of psi becomes what? H bar k times psi. This gives me my P bar to be H bar I divided by I d of dx. Is the construction clear? How do I get the momentum operator? Once I know my momentum operator, then finding kinetic energy operator is very easy. What is kinetic energy? P square by 2m, right? So P square by 2m. So I will have this h bar square by I square times 2m del square del x square. So this becomes my minus h square by 2m del square by del x square. This becomes my kinetic energy operator. Fine. Similarly, my potential energy operator V of psi is nothing but the potential energy in its absolute sense times psi. So this becomes my potential energy operator. Fine. Now I have my total energy operator. So total energy is what? Basically E of psi. What is the energy you know? E equals to h nu, right? That is your h bar omega. We have seen this. So h bar omega times psi. Now again a psi equal to a to the power I kx minus I omega t. So how do you bring out omega? So d psi by dt if you do, so it will be minus I omega times this entire quantity, that is your psi. Fine. Then again h bar dt is your minus I times h bar omega psi. So 1 divided by minus I is I h bar d dt of psi is equal to h bar omega times psi. So your E operator is nothing but I h bar d dt. So once you know this, now constituting your Schrodinger equation becomes very easy, because from energy conservation, kinetic energy plus potential energy is equal to my total energy. Fine. Now if I just use this as operators, what is my kinetic energy operator? I have just found out, minus h bar square by 2m. So minus h bar square by 2m d dx square psi. Potential energy, I have found out this to be V of psi, and this energy I can, if it is non-time varying system, then my ddt does not make any sense. So I write it as E of psi. So this is my one dimensional, it is called 1D TC, means one dimensional time independent Schrodinger's equation. Remembering this is not a big deal once you understand that this is just nothing but your energy conservation. Fine. This is the governing equation that dictates how a small particle will lie in a potential well of this nature. Okay. Now let's copy this. So this is my entire system now, right? Is it clear up to this point how Schrodinger equation came about? Okay. So once you have this idea, now you start experimenting with the actual problem, right? So I see that there are three regions: region 1, region 2 and region 3. So I say that psi is 0 here. This I can directly confirm because an electron cannot be present in this location. Why do I say that? Because the wall of the well, if I keep it extending, this is infinite, right? Infinite potential well. It is as if you are standing in a well which is infinitely long deep. No matter how long rope you use, you cannot be able to get out of this well to the ground, or you cannot be present inside these locations. So probability of finding you or the person who is at the bottom of the well outside this well is 0. So that is why my psi will be 0 in these two locations. Fine. Now I need to check how this electron lies in this region 2. So for region 1 and 3, psi is equal to 0 because these two regions are outside the infinite potential well. If it is finite potential well, then we will see that the case will be a little bit different, right? For example, if you know that what is the height of the well, then you can add a rope and get out of the well, right? Or you can do the Batman stuff, just climb onto the rocks and then get out. Fine. So yeah, for region 2, we need to find out how my psi is, right? Because that is my state variable. Once I know that, everything else will be known. Fine. So for that, we need to solve the Schrodinger equation inside region 2. So let me write the Schrodinger equation. Del square psi by del x square plus v of psi is equal to E of psi. So this V of psi is 0 because why? The potential energy inside this well is lying at this floor, right? That is my 0 level. So V is equal to 0 here. Fine. That means what? Whatever the energy of electron inside this are my kinetic energy. Okay, these are the conclusions I am drawing. E is nothing but your electrons energy that we need to find out. Fine. So now how my equation becomes? Del square psi by del x square is have become 2me divided by h bar square times psi. Fine. This entire stuff I am assuming it to be some constant k square. So del square psi by del x square is equal to minus k square of psi. Fine. So this k, where k is equal defined as 2me by h bar square. You can relate this. For example, this h bar square k square will become your 2me. So your E total energy will become h bar square k square by 2m. You can see, right? This is the same thing at my kinetic, as my kinetic energy is half mv square is giving me. So I can assume that this quantity is giving me the wave number. This k is called the wave number. So I can assume it to be, for the time being, you can assume it to be as just a constant k square. So what are the possible solution of this? One is your A sin kx plus B cos kx. Do you agree with this? So by the way, this psi is a function of x that we are trying to find out because it is time independent and one dimensional. So are you satisfied with the choice of this? So if you are not, just do psi dash x. What it will bring you? K times A cos kx minus kb sin kx, then psi double dash x will become k square minus a sin kx minus k square b cos kx. If I take k square common, it will give me psi x back. So this is exactly the equation this. So I can safely say this is a general solution of the partial differential equation. Fine. Now I need to find out what my A, B and K are, right? Because I have not found it out. So psi of x, I have A sin kx plus B cos kx. Fine. Now I need to find out the boundary conditions. One is my this boundary, another is my this boundary. So I can write psi of 0 is equal to 0 and psi of L equal to 0. How can I write that? Can anyone tell me? What property of the psi x I am using to find out these boundary conditions? Remember that we have noted that psi have to be continuous, right? And we know that psi is 0 in these two locations, right? So at these points, psi have to be equal to the value of the other side to be continuous, right? So that is why from the continuity of psi, we have got these two boundary conditions. Is it clear?
Yes, sir.
Fine. So if it is clear, then let me put psi of 0, that is 0 plus b equal to 0. So your b has turned out to be 0 and your psi of L is equal to a sin kl equal to 0, right? So what about Can A be 0? So this will give me A sine of KL equal to 0. So I am writing that sine of KL is equal to 0 because A is not equal to 0. So from this condition, we have psi of x equal to A sine kx, right? Why A cannot be 0? From this step to this step, I can only write if A is not equal to 0. Otherwise, I am encountering a 0 by 0 situation. Why can A not be 0? My function has turned out to be this now, right? Because B is 0. So if A is 0, if A is 0, irrespective of sin S, my psi will also be 0 always, right? That means my psi of here will also be 0, which cannot be true. Why? It is violating the normalization condition. The particle has to be found somewhere. So A cannot be 0. Is it clear? We'll find out what A will be, but A cannot be 0 because otherwise it will violate normalization condition. Fine. And from that, I can clearly calculate K is to be n pi by L because 0 is sine of n pi. Sine 0 is 0, sine 180 is 0, sine 270 is 0, right? Sine 360 is 0, not 270. 360 is 0, right? Pi is your 360. And what is the value of n? Value of n is starting from 1, 2, 3 and so on. Integer values. N cannot be 0. Again the same issue will happen. If n is 0, irrespective of whatever A is, my psi x will always be 0. Then that will also violate my normalization condition, right? The particle has to be, electron has to be somewhere in the well. Fine. So now my potential function looks like this. A sine k has turned out to be n pi by L times x. Fine. Now I need to find out what is my A. So generally the constant is found out by the condition of normalization. That means minus infinity to infinity psi star psi dx is equal to 1. That is my normalization condition. Now psi is non-zero only inside x equal to 0 to L. So that means 0 to L psi star psi is basically a square sine square n pi by Lx dx equal to 1. So you take a square by 2, 1 minus cos 2 n pi by Lx, right? Then a square by 2, this will come out to be L. This entire thing will get cancelled out because it will be sine 2n pi, sine 0 minus sine 0 will be 0, 1. So your A will be square root 2 by L. So what is your function then? Wave function has become square root 2 by L sine n pi by L times x. So once you know this, every other value you can calculate from this. This is your wave function. Fine. Now in our case, it was mentioned that from E4 to E0, the photon wavelength is 20.9 nanometer, right? So we have to find out what is my energy. So inside the well, I only have kinetic energy because my potential energy is 0. We have seen that. So En will nothing but be h bar square k square by 2m, my kinetic energy, h bar square by 2m, k square is, this is my k, so n square pi square by l square, right? Now E4 minus E1. So if I take everything else outside, so that means h bar square pi square divided by 2ml. So I have 4 square minus 1 square, right? So this is my delta E is h bar square pi square by 2ml times 15, and this is giving me a wavelength of photon wavelength. Remember the photon wavelength of 20.9 nanometer. So for photons or light, I can write this to be hc by lambda, h nu Planck's law is equal to h bar square pi square by 2ml times 15. So this lambda I know. So what I need to find out? I need to find out the length of the well. So length of the well is L, that will be h bar square pi square times 15 divide times lambda divide by 2 times m times h times c. So h bar square you know, pi you know, 15 you know, lambda is given as 20.9 nanometer. If I am not missing, 20.9 nanometer. Then m you know, 9.11 into 10 raised to minus 31 kilograms. H again you know, 6.626 into 10 raised to minus 34 joules per second. And then C also you know, photon, right? Photon speed is your light speed, 3 into 10 to the power 8. If you solve all this, then you will find out the value of L. So if you calculate all this, you will find out that this potential well has the length of your this 0.308 nanometer. Okay, so this is how you calculate quantum mechanical problem, or it is famously known as particle in a potential infinite potential well, right? This kind of problem you can solve in this fashion. Next session I'll give you a real example where these problems will be more useful, right? For example, you have your MOSFET, right? In MOSFET, through the gate oxide, sometimes tunneling can happen, right? I will show you how the potential well looks like and why inside the insulator there cannot be a presence of electron, but it can travel from one place to the other, right? So that is what your quantum mechanical tunneling is all about. And these all are based on the results of this quantum mechanics. Fine. So I hope this will give you some heads up to solve your assignment problems, and we'll continue from next session. If you have any query, I'll be happy to answer. Is it clear? The potential in an particle in an infinite potential well, how we determine the Schrodinger equation. It is nothing but your energy conservation. Once you are familiar with this kinetic energy, potential energy operators, right? You have to just always note a general wave, take any general wave, and then compute your way back to what your momentum operator, potential of kinetic energy, potential energy, and energy operators are, right? Any question? And then you solve this, divide the major problem in multiple regions, right? Divided by boundaries. Once you know your boundaries, divide the overall problem into sub problems, sub regions, then add the boundary, use the boundary conditions, and use the properties of this wave function psi. Then it is nothing but a solving of your semester 3 partial differential equation problem, right? If you do not have any doubt, so let's end the session here, and hopefully you will come more prepared from next session, or you will have more questions which I can help you answer with, right? Okay, so see you next Saturday then. Bye.